Welcome to another video for Stat 420. In this video, we're going to begin talking about predictor interactions. We're going to do it on a very simple scale in this video. We're going to stick with kind of having a binary predictor, having a dummy variable with two categories, and talking about how to decide whether or not that dummy variable might interact with another predictor in our model. So as a reminder, we talked about in the previous video this idea of adding a binary predictor with an additive relationship with the response variable. So in other words, we have some kind of a scatter plot. So maybe we have like an x1 and y, where we have a numeric predictor with a numeric response, and we have some kind of relationship. But we might notice here that maybe there's two different categories as well. So maybe this is one category, this is kind of another category. And if we kind of keep track of that, we do notice that if we're paying attention to that binary predictor here, we can use that to predict the response variable even better. So instead of just fitting kind of a general best fit line, I can actually essentially fit two different lines, one for each level of this factor variable. And I guess that should actually be blue, but oh well. So instead of just one general best fit line, I can pay attention to this other binary predictor that shows some kind of additive constant difference between the two levels with relation to the response variable. And so when these factor levels are parallel like this, it means we have an additive relationship. It means that this variable doesn't interact with x sub 1 here. So this right here would be additive. So there's a constant difference. It's not related to x sub 1 here. But there's another story where this factor variable does actually interact with the predictor in terms of how well it predicts the response variable. So I could also have a situation where maybe I have some data that looks kind of like this. And I'm making these like very strong correlations just to kind of make a point. Most of the time, I feel like we're working with data where the correlation is not nearly as strong. But I feel like it's a lot easier to see what's going on if we kind of do this. So in this case, this would be an example where I have two categories, but the best fit lines really aren't parallel to one another. They're actually, they actually have separate slopes here. And so that means that this binary predictor not only tells me something about the response variable, but it also interacts with x sub 1 down here, meaning that the effect of this level, whether like how this level plays into my prediction actually depends on the value of x sub 1 down here. Because we might notice that when x sub 1 is high, there is a bigger difference here, right? So there is a bigger effect going on between these two levels. But when x sub 1 is smaller, that difference kind of goes away, and the factor level really doesn't matter that much. And so when I think about kind of modeling this predictor variable, I have to create my model a little bit differently when I have a situation like we do on the right, where we have an interaction. So the difference depends on x1 here, as opposed to being kind of independent of x1 and just having this constant additive relationship in our model. So we're going to go back to some data we've seen before, and this is the professor evaluation data where we're looking at predicting student evaluation scores for a professor based on a beauty score that professor had in a particular study that was conducted here, where some students who didn't necessarily take their class, there's just a couple students were kind of picked into this study to look at pictures of different professors and assign them a beauty score from 1 to 10. Then what we did was we took the average beauty score of these students, assign it to that professor, and then we look to see how well that beauty score correlated with their overall student evaluation scores. And so the one thing we're kind of wondering here is, can we better predict a professor's evaluation scores based on their beauty or based on other factors, I guess. And so here we notice that we do have some evidence that there's a little bit of a correlation. It's not much, but we do seem to make slightly better predictions when we do know their beauty score. So that's kind of interesting. It doesn't mean that this is the cause. It doesn't mean there could be other confounders that are explaining why this is true, but it is a correlation. It does help us make a better prediction at least. So one thing we might also wonder is the role of gender in this. So if we're paying attention to whether we're looking at female professors or male professors, does that give us another layer of prediction here? Does that give us a better estimate of evaluation score if we also know the professor's gender? So one option we have here is to basically treat this as an additive relationship, just like we did before, where we have y hat equals some intercept plus the relationship with beauty average. And I guess what I'll do here is I'll call this actually what it is, and that's eval scores. So our best prediction for evals is going to be some intercept plus this relationship with beauty score plus this dummy variable for gender. So basically, if the professor is male or if the professor is female, that determines if we have some constant difference to add. And basically, this term is simply adjusting the intercept. So if gender is, in this case, male is the one that got assigned to the category 1. So this kind of switched from before. So now male equals 1, female equals 0 in this example. Oops. So it means that when the professor is male, beta 2 is going to be what gets added to the intercept. So it kind of adjusts that intercept. When I think I said beta 2, when x sub 2 equals 0, when gender is female, then this term goes away, and the intercept just kind of stays as it is. So this helps us decide if there's a constant difference, a constant addition to create here based on a gender effect. However, we have another option here, and that is to model this with an interaction, meaning that, that the effect of gender might actually depend on beauty score. So it's not just that gender creates some constant difference here, but that the difference based on gender might actually depend on the beauty score of the professor to begin with. So in this case, if we create a least squares model and fit this model with those parameters, we notice here that there is a larger gender discrepancy among the more beautiful professors. So professors who are getting higher beauty scores, we notice that the male professors seem to be doing better on average than the female professors, whereas when we're looking at lower beauty scores, that difference gets a little bit smaller, not a whole lot smaller, but we do seem to notice a little bit of a kind of a convergence here among the lower beauty scores, whereas we seem to see more divergence between genders at the higher beauty scores. So what we're going to do is, do I have room for this? I have room for this over here. I meant to actually make this go away, so this is something I didn't mean to have on here. Actually, you know what I can do? I can write up here. So essentially what we're doing is, let's see what I'm going to do. I'll write it generally first. So it's going to be y hat equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2. And this right here is what we call the interaction term. So it means that depending on the gender of the professor, right, because this is going to be either a 0 or a 1. If it's a 0, this goes away as well. If this is 1, though, we are going to adjust our slope value, right? Because, so if this is 1, then I'm going to have beta 3 times x1 plus beta 1 times x1. If you remember from, I guess it's algebra 1, like terms can be added together. And so essentially what I'm doing is I am adjusting the slope value depending on the gender. So for example, if gender is male, if male is assigned to 1 here, and beta 3 is a positive value, a positive number, that means that I am making the slope steeper. I'm making it larger when gender is male, whereas it is just going to stay like this when gender is female. And then this term right here is still functioning the same purpose here. When gender is male, I adjust the intercept by whatever this value is. So by adding an interaction term, I can now adjust both the intercept and the slope based on which category is true here. And before we get too far in this, just kind of a quick reminder that we still have to judge if this interaction term is doing anything. I can make this graph, and this graph can make me feel pretty good, but ultimately I'd like to make a probabilistic calculation on how confident I am that the interaction term is adding something to this model. And so I can still use this t-test if I want to. The t-test gets a little bit trickier the more terms that I add. But in this case, the t-test, if I'm only comparing the addition of the interaction to not having interaction. So actually, let me go to this because I think it's a little bit easier to see everything here. So what I did here is I created an ANOVA where I was comparing an additive model to an interaction model to see if I was explaining a statistically significant amount of variation by making that interaction term included in the model. And so I get a p-value of 1.5%. So that gives me some confidence that I am kind of maybe doing something with this interaction. I mean, it's 1.5% is not super tiny, but it is tiny enough that I feel pretty confident that this is not being explained by random chance very well. You will notice, by the way, that this matches the t-test p-value because, again, this is measuring the statistical significance assuming that we already had these other terms in the model. So if I'm making a comparison between two models where there's only one term difference, then the t-test result should match the f-test result. F-test results, though, will be a little bit different and give us more information if we're comparing models where we have more than one term difference. So if we're comparing models where the terms are different by 2 or 3 or 4 terms, then I can't just look at the t-test results to decide that anymore. But if it's only a one-term difference, the f-test and the individual t-test are going to come out the same there.